Okay, we're going to get going. Welcome back to class, everybody. Today we're going to start our discussion on muscle. We'll see that where that takes us. I have a couple of things that I would like to, just like small announcements. On September 28th, that is the holiday of Yom Kippur in Judaism, and I will be at virtual synagogue with my mom and her husband, so I will not have class on September 28th. I will have class every other day that we're supposed to have class. Maybe what I'll do is I'll go through the lecture and I'll post it for you, but we won't be meeting synchronously, as they call it. We'll have to meet asynchronously that day. Let me share my screen. First of all, good morning, Emily and Jose, Greg, and John. Nice to see everybody.
Morning.
My man. All right, let's share the screen and let's get going. So I've added a couple of things to the Blackboard class today. This morning I added these two PDFs, skeletal muscles and the muscular system. Those would be the two chapters. I believe skeletal muscles is the chapter from the book that we have suggested. I'll even go like this, edit, and I'll just go chapter 3, so you'll know what that is. And then the muscular system is another chapter from a different course textbook that I have that I think that does a really good job at reiterating and re-explaining some of the concepts that chapter 3 got to. I'm pretty sure that this assignment here that has been posted since the beginning of the semester is due September 25th. And I also tried to make this October 9th thing. Let's fix this right now. I'd like to make this due a little bit later. Assignment number 2. I'd like to make this due, I thought I had put September 11th. Yeah, I think I switched it to October 9th over the weekend. So you should have plenty of time to get these things done. I'm sure that you could start stress strain curves and stuff like that now. If you need anything, let me know. And then assignment number 1 is due September 25th. I'll probably end up giving you more time on each of these assignments as well, but we'll get to it when we get there. So that's what we have in terms of new content on the website today. And then I'd like to try to get into this, this presentation. So let me grab this and move it down. So today we're going to be talking about, all of the tissues in the body are unique, but today we're going to be talking about one of the more unique tissues. Now remember that muscle is the only tissue that can create an active force. So that's kind of an interesting thing there. Let me try to get this on. Well, I think that's better. Man, all these little... All right, so muscle is able to produce a force. And that's interesting because forces cause masses to accelerate. So isn't it great that muscle, the very tissue, can factor into these Newton's laws of motion? Today we'll talk about the physiological hierarchy, or how muscle is organized similar to ligament and tendon. And the main thing there is that that's going to limit blood flow and vascularization throughout the material, which is going to make it harder to keep it into the elastic region, or to go at least back into the elastic region and do what biological materials do in the sense of healing. We'll talk about the sliding filament theory. I'm sure everybody's heard of that. Jose, you heard of the sliding filament theory? Jasmine, sliding filament theory, you know what that is? All right, why do they call it a theory? What's this word all about right here? Because if it wasn't theoretical and it was fact, then it would say muscle filament fact, but it doesn't. It says theory. So we have to kind of postulate what that means. And if you go into all of the kinesiology textbooks that are out there, old ones, new ones, they'll talk about the sliding filament theory, but none of them will say the sliding filament fact. So we want to have a little bit of a discussion of that. Then we'll talk about types of contraction, isometric, isotonic, eccentric, concentric, what's the difference, and what are those contractions doing? Then we'll talk about how each of these types of contractions can absorb or generate power. Actually, isometric contractions are more relevant to the discussion of stability of joints, so we'll talk about that. So by the end of the day, I would hope that everybody here can list the characteristics of muscle, explain the difference between the types of muscle contractions and maybe what their function is. Describe, or then there's a difference between explain. I want you to describe how actin and myosin interact, and I'll give you a description and then I'll give you an explanation of something right now. I could take this pen. I don't know if, like when I do this, John, can you see, like, you can see me doing this, right? All right. I take my pen and I move it from here to here, all right? I could describe it like it was on a conveyor belt. I could describe it like it was on a windswept leaf. I could describe it as if it was on a canoe and went from this direction to that direction, but I cannot explain the motion of this pen with any of those terms. A description can be metaphorical, it can be poetic, it can be hyperbolic, it can be allegorical phrasing, all right, but an explanation is different. An explanation is going to use, say, for instance, pincher mechanics in my fingers, and it would use, say, ATP and muscle contraction. You would have to talk about how my shoulder is probably creating some type of a lever system here. That would be an explanation of how this thing moved. That's more difficult than a description. So we want to talk about the description of actin and myosin interacting and maybe an explanation. Then what we want to do is be able to take a look at a simple activity or example and define the muscles that are involved, which ones are the prime movers and which ones are working eccentrically against that prime movement to absorb power. But again, I don't think that I'm going to overly focus on the anatomy and physiology of muscles in terms of their origin and insertion. So I think that we just have to be aware of, if I'm giving you an activity and say which muscles are involved. I mean, I don't even know all the muscles involved in everything. So what I do is I go to YouTube or I go to Google. So as long as you have a way to identify the agonist and antagonist, the agonist and protagonist muscles, and then use the tools that you have to try to figure out what's going wrong, I think that that's pretty much where we can go with it. I'm going to stop the share for 1 second because I'm not sure if I pressed record. I am recording. All right. All right. So let's go back here and let's just get into this, this lecture. So these are the characteristics of muscle. Muscle is contractile, or it has contractibility. And by that, what we mean is that it has the ability to produce a force. It can shorten and produce the force, but it can also lengthen and produce the force. All right, in that case, it's not really producing a force, it's absorbing a force, but we'll get into that in a little bit. Muscle is extensible. It can lengthen, it can extend, much more extensible in many instances than ligament or a cable. So muscle has the ability to extend. The actin and myosin cross bridges, or the connections between the two, are not fixed. So they can move away from each other and the muscle will lengthen. And the actin and myosin, when it interacts, is going to pull one towards the other in a concentric contraction, and then the muscle would get shorter. when a muscle lengthens, because it is a valid, viable tissue on our planet, it is able to have characteristics, and those characteristics, because of its function and therefore structure, are that when the muscle does lengthen, it has a bit of an opportunity to stretch. And when materials stretch, like my rubber band stretches, it stores elastic energy to some extent. And that elastic energy is also going to be able to allow that material to hold some type of tension. And tension is a force. So that material is able to withstand a force because of its passive elastic component itself. Now, muscle has two different abilities. It can actively do something, and when it's active, it creates a contraction with actin and myosin. But muscle, if I took your muscle off of your arm and I, nailed it to the wall and grabbed one side of it, I would be able, now that muscle would be dead. It's not in your body anymore. It's not being interacted by your brain or your spinal cord. So that muscle is now not alive, but I could still create a passive tension by pulling it. So muscle has an active component and a passive component. And we'll talk about those a little bit later when we talk about the length tension curve. Now, one of the things that we should say is, the whole point of this, I think, course is for us to think about how the brain is making all of this stuff happen. All right, how is the brain able to make all of these little cross bridges and muscles interact in the right sequence of muscle firing, in the right duration, intensity, and we'll look at the structure of muscle. It is such a finely detailed system. There are same thing, muscle bellies and the epimysium and the paramysium and motor units. And so how is the brain able to interact with all of the motor units and muscle fibers all at the same time and not make too many mistakes doing it? So we'll have to talk about the sliding filament theory's weaknesses in terms of explaining some of that stuff. In any event, a muscle also is distensible. It swells. So if I make a muscle with my bicep will widen. So not only does it lengthen, but it also will widen. And then muscle has nerve endings. And because of that, it can have a sense of irritability, or it responds to external stimuli, irritation. So therefore, its irritability has neural consequences to stimulating muscle. Again, muscle is this particular hierarchy where you have the belly of the muscle, but within the belly of the muscle, you have little fascia or tissues that separate other bundles of muscle. The outer layer is the epimysium, and it's in this epimysium here that you're going to get most of the blood flow. Now, the blood flow isn't going to go into the individual myofibrils. It can't get that close. So you'll notice that you have the epimysium here, and then the inner layer is the paramysium, and then the endomysium, and then smaller and smaller until you have a muscle fiber, which is a sarcolemma, a single muscle fiber. And you'll notice that there are multiple nuclei along the border of this muscle fiber. And that's important because changes to the DNA and RNA in these nuclei, because of the endocrine system and testosterone and growth factor, can stimulate change not just in one area of the muscle fiber, but along the muscle fiber, and result in total, it can result in a more effective production of protein when muscles are trying to grow, because you have more opportunity for steroidal interaction with the muscle cells. In these myofibrils is where you have the actin and myosin is going to be intertwining. So what we believe is happening is that there are these actin and myosin filaments that are intertwining, and they're intertwining because of impulses, action potentials sent from the brain, from an area of the frontal lobe or other areas of the brain. And the action potential will travel down the appendicular nervous system and interact with motor units. And a motor unit is the last motor neuron in the muscle fibers that it's touching. Some motor units are big, some motor units are small. More intense activities are probably going to use more, a greater number of motor units. Your eye would have, the eyelids in your eye would have very small motor units, but your quadriceps and your glutes would have huge motor units. And the action potential comes into those muscle fibers and causes a release in acetylcholine or dopamine across the synapse of that muscle fiber. And here, maybe I can even do this. So you have like your muscle fiber. This is going to be like the end of a neuron. This is an axon. And then you're going to have like your muscle is going to be here. And then in your muscle, there's going to be, in your muscle cells, there's going to be receptors for these motor neurons. And then in order for the action potential, which is coming this way, to interact with this muscle fiber, which is here, then there's things that need to jump the gap between this neuron here and the receptor for that neuron on the muscle fiber. And usually what's going to happen is things like dopamine and acetylcholine are going to travel across this gap right here. And when they travel across the gap and are taken into the muscle fiber by the receptors in the individual fiber, then you have actin and myosin, which are like, so now your muscle's going to, whoopsies. Let's just keep that there. Undo. Draw, no. So then your muscles are going to have these little striations on them that look like this. And it's within these striations here, if you look at the muscle fiber, these are called Z discs. And then if you look and take one of these things and you blow that up, erase everything, undo, clear. If you clear all drawings, if you do that, then what's going to happen is you're going to have this draw. You're going to have this a muscle fiber that kind of looks like this. This is the very simplest way to explain what actin and myosin are doing. So you have your actin, and then you have these little myosin heads that are arranged like this. And at the end of each one of these things is going to be a little troponin or tropomyosin receptor. And when these troponin and tropomyosin receptors attach to the myosin, then what happens is instead of the angle, and you have other myosin that's like this, and so forth, all the way down here. I don't want to dry them all. When the troponin and tropomyosin touch each other, it makes the angle of this filament here switch from that angle to this angle. It switches, like it creates this change in position from here to here. And if all of these change the angle, then what happens is it's gonna, and same thing as all of these ones change their angle, then what's gonna happen is this side is going to slide that way, and the other side is gonna slide this way, and it's gonna pull this whole muscle section together and crimp it in the middle. So the sliding filament, this is called a cross bridge. This is a troponin, or this is a myosin cross bridge, and at the end is this little chemical called troponin, and then you have the actin, and the actin is going to be this long, thin strand in the middle that has these little balls, these little receptors all along it, so that the troponin on the other side, you would have other cross bridges here, and the whole muscle kind of folds together, similar to how like a towel, when you twist it from one side to the next, would change its length as it spirals in on itself. Now, that's as close as I can get to explaining to you in 3 minutes what the sliding filament theory does. If you look in every textbook, you'll find it. Every textbook, you're going to find the sliding filament theory. You're going to see, I don't know how to get off of this mouse. That is one heck of a problem. So I don't know how to explain that any more succinctly, but it's still theory. If you take a look in any textbook, it's going to say sliding filament theory. So what we have to do is maybe consider why it's still theoretical. And I think that discussion frees you up to think about movement in many different ways, and how you particularly buy into a theory of movement is not going to be the same as mine. There are many different movement theories out there. There's the brain does it, there's God does it, it's luck, it's instinctual, it's reflexive, it's based on the systems in the environment, optic flow, it's a perception action coupling, it's a dynamic system, it's ecological psychology, it's cognitive psychology. These are all very, very different and competing theories of movement. And if I read things like Ulrich Neisser, and I don't mean to name drop authors here, but this is an author who wrote about how the brain separates motion into schemata and different motor programs, and your brain takes out those programs similar to like a computer would. And he'll talk about cognitive psychology and how the brain is intricately involved with all of the decisions and all of the ways that you move. But then there are other theorists like James J. Gibson, who came out with stuff in 1953 and talked about ecological psychology. And when we talk about biomechanics, we're not really going to talk about biomechanics in the sense of the word, but I'm going to try to open your mind up into thinking about movement differently. All right, I find it very implausible that the brain is controlling every actin and myosin interaction in every muscle at every time. And Jose, I don't see, like, I've watched you for the last 10 minutes. You didn't make any mistakes. You didn't fall over. Your head didn't fall forward to the side out of control. You know, you didn't fall to the side into the wall. You don't seem to make mistakes when you move. Jasmine, I see that you got your hand on your chin. How did you get it there? You didn't think about that. You didn't think about rubbing your thumb right there either against your chin. You were thinking about what I said. So there's an aspect of movement that is, I don't think is the brain doing it. So then if you have a theory of movement, and I'm going to say, I don't think it's the brain doing it, then as your professor, at least I have to give you what I think is my theory and why I believe in that and what makes me feel confident with that. But it's a different theory than the hierarchical brain does it theory. So either you're going to buy into the brain does it, and if you do, there's going to be philosophical issues with your argument, reasons why your argument aren't factual, why they're still theoretical. But if you ask me about my theories, I'm still going to have the same problem because it's still theoretical. The key is for you to buy into a theory, whether or not it's all right or all wrong. Understand the theories enough so that you can make your own decision, because then when you can do that and understand the power and the strengths and the weaknesses of each theory, then you can start to think for yourself. And you can start to say, why is it theoretical? So I don't want to get into a statement necessarily about, to me, why or what, but it says it right there, sliding filament theory. Now, if you take a look in the book is going to say that the brain sends an action potential. That's where the whole theory breaks down. The book never says where the action potential comes from. It just says that the brain sends an action potential to the muscle. Okay, so now the problem with this is there's no explanation of where the action potential comes from. Is it being created in the brain? How fast is it created? How many are created all at the same time? And all of a sudden it starts to break down. What it does is it starts to maybe start this philosophical issue called infinite regress. Like, if the action potential happens in the brain, was there some type of brain in the brain that determined when the action potential should be delivered? And then you have this infinite question. Well, if there's a brain in the brain, does that brain have a brain? Does that brain have a brain? And then if everything is based on the brain, then you have to explain how the brain is making all those decisions. Is there a decision-making center in the brain? So that's a philosophical question that's involved with the word homunculus. And the homunculus in motor theory is like when you have like this little, like if in Men in Black, like the head of the alien would open up and then there would be a little teeny alien in there kind of running the show. That's a Latin word called the homunculus. And it implies that like if that thing, that center in the brain that's making decisions for the brain, all right, does that thing have a brain? Is there a control center that's iteratively smaller and smaller and smaller? And you'll never be able to really answer that question. So there's other philosophical questions like context condition variability, the degrees of freedom problem. We're not going to get into it right now, but we will talk about all of this stuff. And hopefully you'll have an opportunity to develop your own theories of movement when we're done, all right? Any event, actin and myosin intertwine according to this theory. Here's these are called your, the filaments right here. You have your actin and myosin. I don't think, it's just a drawing, so I don't think you need to know whether or not that's actin or that's myosin. But in any event, these Z discs here, this is, I guess, a better one. So you have these myosin filament and actin filament, and you'll notice that the myosin filament here, let me see if I can, there are these cross bridges right here with these springs on them. And when these little heads attach to the actin heads here, then it causes these two molecules, troponin and tropomyosin, to intertwine, and then this filament here rubs against that filament, and this cross bridge right here flips this filament that way, and that's how a muscle contracts. All of this motion right here, movement of that cross bridge and that cross bridge, that's motion. And if you have this cross bridge here moving, a nanometer, but you have thousands of them moving nanometers, then your muscles are going to change their length pretty rapidly or pretty extensively potentially. But this right here, the movement of this thing requires energy. And where is that energy going to come from? Jasmine, you know where that energy is coming from? The energy needed to change the position of this cross bridge, this myosin cross bridge from here to there. You know where that comes from?
ATP.
Heck yeah. Right, so now all of a sudden everything is coming together. Now, if you think about it as an actin and myosin system, a system is unique. And what's happening here is they'll call it the muscle skeletal system, the cardiovascular system. And when we talk in biomechanic lectures about systems, we'll talk about the benefit of systems and what you get out of making a system out of things. Now, this looks like a big system to me of molecules and filaments and energy and ATP and oxygen and water and glucose. And so I think that if everything works together as this huge system, then we have benefits in thinking of it that way as opposed to a hierarchical plan. All right, anyway, in order for your muscles to contract, all right, they get shorter in some extent, all right? Sorry. In concentric muscle contractions, your muscles are shortening. So when the actin and myosin intertwine in such a way that the Z discs, which make up those little individual sections of the muscle fibers get closer together. All right, that's called a concentric. Con is with and center is centric, with the center contractions. So when this part of the muscle and this part of the muscle go towards the center, go towards the belly, and they make the muscle distend, that's called a concentric muscle contraction. Now, a concentric muscle contraction is the opposite of an eccentric contraction. Now, why is that the case? Well, a lot of times your function is going to be different. The function of a concentric muscle contraction is to generate power. We would all agree. Now, if you think about it, if you hold a weight in your hand and you are pulling the weight, all right, in this direction here, you would be pulling that weight against the natural tendency for gravity to pull the limb, the center of gravity of this limb down, the center of gravity of your hand, coupled with the weight of the barbell trying to pull your hand down like this. All right, now there's a weight here. This weight is acting at a perpendicular distance, you know, to the axis of rotation. So it's I don't know, I don't want to get into that. Maybe we'll get a little bit, but it's creating a torque for your arm to go in that direction. Actually, your bicep here acting at this moment arm is going to create, if the weight is moving this way, then your arm is creating a torque in the opposite direction. So we'll call that the torque associated with the muscle, in the opposite direction of the torque associated with the limb and the torque associated with the external weight. Now, if the total torque of the external weight and the total torque of the lower limb and hand in these directions here were stronger than this muscle pull that's creating a torque in that direction, then what would happen to that limb, Jose? And let me try to make it a little bit clearer. All right, let me erase this and just make it just a little bit clearer. So if I go like that and I say, no, I don't want to use that color, draw, and I'll go use this color. So you have the weight right here. If the weight is still on this side of the axis of rotation, see now the weight is just on this side of the axis of rotation. So there will be a distance here associated with where the weight is, and it would make the weight want to drop in this direction. But then there's also other aspects to consider, like not just the weight, but the weight of the hand would also be dropping the hand in that direction. The weight of the limb here would also cause a torque in that direction. All right? If all of these torques here are stronger than the torque that the muscle is providing in that direction, what is the arm going to do, Jose?
So obviously, if you don't have that strength, I feel like your arm, you won't be able to pick it right back up. Like if you're doing you're saying like if I'm doing the bicep curl, you're saying if the force and like the weight is heavier and like my muscle don't have that strength, then like I feel like I wouldn't be able to, like when it goes down, I feel like I wouldn't be able to pick it back up.
It's exactly right. The torque, the combined torque of the weight, the hand, the limb, and how gravity is interacting with that system, with that lever, is overcoming the amount of muscle torque that I can provide in that bicep. So gravity, like Jose, and the external forces on that arm are going to be the reason why the arm eventually doesn't rotate in this direction like we want, that the arm would rotate in that direction now. That's not a cognitive thing. That's not a cognitive reason for that limb to be opening up like that. That is because if the limb is overcome by the force of those things and can't provide an appropriate muscle contraction to lift the weight, that's the reason for the extension there. So instead of thinking about the brain doing everything all at once, everything, maybe we can just think of the brain doing what it needs to do some of the time. In this case, the rotation of the limb, as Jose mentioned, is due to the fact that the green torques are out or are stronger than the red torque. And the motion happens on its own. In that case, this concentric muscle contraction couldn't generate enough power to overcome the force due to gravity. All right? A muscle contraction that's concentric not only gets shortened, and not only does it distend, but it's always in the direction against gravity. You're doing a bicep curl against gravity. Your quads are working to generate power to overcome the grip of gravity. Does that make sense? All right, now an eccentric muscle contraction, yeah. I could explain it like it's when the muscle gets longer. Now let's go clear all of this. Now what's gonna happen is you have the weight, and the weight is creating a torque in this direction. It's creating a torque because there's a mass to it. And that mass is acting at a distance away from the elbow here. And this distance and this mass and the acceleration due to gravity are going to create a torque in the downward direction, a torque associated with the weight. Now, the bicep is firing in this direction, pulling up with its pretty small moment arm in whatever force and torque it's creating. So that's the torque due to the bicep, and that's pulling the arm in that direction. All right. Now, in an eccentric muscle contraction, the muscle is still contracting, but the weight is right now overcoming the force of the muscle contraction in this direction. So the weight is being lowered. It's being lowered with gravity, in the direction of gravity. So really what this eccentric muscle contraction is doing, as the muscle continues to contract in this direction, it's just not contracting enough to overcome this force, or it's contracting enough to let this force create this torque actively by lowering the weight down, as opposed to passively when the weight just drops down. So an eccentric muscle contraction, all of the muscles are eccentric. I think of that like sometimes people like shy away from eccentric people. So it just helps me remember that an eccentric muscle contraction is when everything goes away from each other. People just kind of like are at the fringes. So the muscle fibers are eccentric. They go away from each other, the muscle lengthens, but it's still providing an active torque. All right? That's gonna always be against the direction of gravity. But that muscle here, instead of creating power like it would in a concentric muscle contraction, it's absorbing power. So that's interesting, because let's go back here. This is generating power. A concentric muscle contraction is generating power. All right, which pedal in your car generates power? Jose, you're on mic. May as well just keep asking you questions.
All right, keep shooting at me. If I got the answer, I'll go get him.
All right, I'll ask the question one more time, okay?
All right.
You're in a car.
I'm in a car.
You want to generate power. What do?
I press the gas.
Heck yeah, dude. Okay.
Yep. Press the gas and make sure I got gas on my tank.
Okay, so you have to be able to press the gas pedal, right? And that's how you make power in a car. And you have to have fuel. You have to have ATP.
Yep.
Okay, so it's concentric contractions that are going to generate power. It's the gas pedal. Now, how would you absorb power in a car, Jose?
How would I absorb?
How would you absorb power that you don't want? I'm putting this
Uh,
on you. It's on you right now. You're in a car. There's too much power. How?
so I either let the gas go so it can slow down itself, or if I have way too much power going on, then I gotta hit the brake so I can slow down.
Exactly right. Okay, so when you want to create power, you hit the gas, and when you want to absorb power, you hit the brakes. Now, you can't hit the power when you got to hit the brakes, and you can't hit the brakes when you got to hit the power. If the timing is off between those things, what happens, Jose?
If the timing is off,
Between the power, the ability to push the gas pedal, and the ability to put the brakes on, what happens if there's a mismatch in the timing of those things?
well, you can either drive into something if you don't brake like on time, or if you generate way too much. Well, if you generate too much power, you can crash into something because you obviously not slowing down. And then if you brake, like when you're not supposed, like let's say you're going 65 and you put your foot down on the brake, like all the way down, you're probably most likely to almost hit your face with the front window, with the windshield.
There is a big result of a mismatch in timing between the brakes and the power. What happens if the brakes aren't good? What happens if the gasoline isn't good? All of a sudden, there are so many different ramifications of the physiology of a human being and the ability to have enough ATP. So if your eccentric muscle contractions are absorbing the power, they're the brakes. So that's how I think of the concentric contractions are generating power. The eccentric contractions are absorbing power, but they're the same muscle. So your muscle is doing both things. When you look at your anatomy textbooks, it will say muscle action. And it will usually say the bicep is going to flex the arm. It's also important that you remember that it also slows down arm extension. So your muscle is the gas and the brake. That's pretty unique. And the timing at which the gas pedal and the brake pedal is very important. Imagine if you had a symphony of people, 10, 100 people, all the most amazing musicians that you've ever had, that there have ever been. If you give them this musical piece and you say, John, hey, you have 15 minutes to play it. Make it sound as best as you can. Now, most likely they're unbelievable musicians. Nobody really needs to practice too much. They would play it, but it wouldn't sound as good as if they practiced it maybe, 15 or 20 times and all got in sync with each other. And everybody knew when to come in and when to stop and how intensely to play their musical instrument and how, quietly to play it. All of a sudden they would kind of become in unison with each other. And then the flow of the music would be like right in on it, like, and some bands can get that way. It's also the same thing, like you watch the Tour de France right now, and they're like, it takes a little time to get into your self-preferred beats per minute frequency, but eventually your body emerges with these patterns that are combinations of these eccentric and concentric muscle contractions. So in your theory of motor control, whether or not it's hierarchical or dynamic systems theory or open loop motor control theory, you have to be able to account for that timing. Where is that timing coming from? Is that your brain doing it? Because I'm not thinking of things like that. So what's making that happen, and where does the timing come from? And it seems to me like the timing comes from practice, repetition, using your body over and over and over again. And what happens is you start to reach a resonant frequency. You start to kind of use your body in the most efficient way to save the most amount of energy and do things with the least amount of effort. And I don't mean that in a very negative way. I mean it in a physical being moving and getting energy through gravity, an environment that has, you know, true characteristics to the material that is part of that environment. You know, so how does that timing between the concentric and eccentric muscle contraction ability to create power and to absorb power time itself? That's pretty astounding. That's why a lot of this stuff is theoretical. All right, let's keep going. Now, an isometric contraction is when the muscle stays at the same length. So the torque associated with the muscle the torque associated with a muscle pull in this direction is equally balanced by the torque associated with the weight in that direction, the hand in this direction, and the weight of the forearm in that direction. All right, and what an isometric contraction is when there's the same distance or the same measurement of the muscle fibers throughout the contraction. All right, that's a stabilizing effort where the bicep is going to fire in this direction, but also probably to stabilize the elbow joint, the tricep would also fire in that direction as well. And that means that like the elbow would compact itself and reduce the joint angle and the movement throughout the joint angle. So that's an isometric contraction, and we'll talk a little bit about that later. All right, let's keep going. I'm having fun. So this creating and dissipating power not only needs it to be timed well, but the creating needs to be strong enough, and the eccentric dissipating or power absorption capabilities of the muscles also have to be worked or strong enough or happening at the right time, or else what's going to happen is the muscle is going to change length too fast for it to be able to withstand, and the muscle is going to tear. All right? Now, when we think about muscle contractions and going to the gym, we try to create power a lot. We try to do bicep curls and squats, pushing away from the ground, away from the ground, away from the ground, freeing ourselves from gravity's clutch. All right, but remember, those are all going to be working your concentric muscle contractions. So you're going to get really good at generating power. But you got to get also really good at absorbing power. So doing your negatives, going down is just as important as going up. Using your muscles as a brake is just as important as using your muscles as a gas. Right? So you have to have a good brake pedal, and you also have to have a good gas pedal. So when you're doing your rehab and prehab and knee rehabilitation for everybody, remember, jumping down off of that trainer's table for the first time after knee surgery, that's not a concentric muscle contraction. That is an eccentric muscle contraction of the quads and hamstrings as you lean forward. You know what I mean? So you have to be able to think of muscles in not just in the fact that when they contract concentrically, they get smaller. It's what is that smaller doing? What is the functionality of it getting smaller? And an eccentric contraction isn't when it just gets longer. What it's doing is it's absorbing the forces, and we're always under the force of gravity. So your ability to fire your muscles eccentrically is incredibly important in terms of things like walking and running. You know, because what happens is the muscle absorbing the force due to the body weight as it hits the ground, and the ground reaction force is going to make the whole body fire eccentrically, storing elastic energy, because when the muscles get longer and fire eccentrically, they store elastic energy in them. And then what they can do is release that energy to save and conserve total energy. Potential energy changes into stretch energy in the muscle fibers, and that energy is released in some extent. And sometimes this muscle absorption and saving energy activity, especially as the muscle fires isometrically, increases its stiffness and allows the tendon that's attached to the muscle to stretch, which is an elastic band. All of a sudden you have this activity that becomes very energy efficient, because it's using spring energy as opposed to ATP energy all the time. I'm having fun. So something like running is not just run across the surface of the earth. What it is it's an ever exchanging balance between eccentric and concentric muscle contractions and isometric muscle contractions, to allow for this pendulum that has forces and ground reaction forces and friction between the foot and the ground, and all of these axes of rotation, all generating, when that knee is bending, her left quadricep is extending and stretching, storing elastic energy. And that energy is going to be used to fling that left leg forward into the swing phase of the step. Now her right foot at impact right here looks like she's going to impact the forefoot, hopefully. And that's going to allow for that gastrocnemius on that right leg to stretch and store energy. That's going to make it so that that right leg and hip fling over the back, like the top of the right foot, but it's also going to force the plantar flexion of the right foot into the ground, which is going to force her foot into dorsiflexion and stretch her tibialis anterior. And that tibialis anterior is going to release its energy, and it's going to make it so that the lower leg swings forward through the stance phase. This is all an amazing timing between concentric, eccentric muscle contractions that are absorbing and generating power. How is that happening? If it's hierarchical motor programming theory, I want you to explain it to me. If you can't, you're going to have to figure out why you can't explain it, or find a different theory that you think might explain it better. Now, what I think that's pretty cool here is you have certain forces that are working at each other constantly. Number one, gravity. If there's no gravity, this woman wouldn't run like a pendulum. But she runs like a pendulum because she's able to create torque. And that allows things to swing on an axis. And that has an arc. And the system here is using the torque of her upper body, turning her shoulders towards me to store energy in her belly. She's also swinging her arms, which is going to store energy in her delts and allow for a greater stride. This looks like a system of muscles and torque and gravity and the earth and the being in its whole system form, as opposed to anything else. This is way too complicated and beautiful to happen. And now, Jasmine, people run the marathon. Not only are they able to get this motion to happen successfully one time, the symphony of like human movement that is on that screen right now, not only can they do that one time, but stride after stride after stride for 26 miles in a row. not thinking about it. You're not thinking about step to step to step. What do I got to do here with my plantar flexion? How am I going to swing my arms forward? You just get into the zone. And it just like it emerges from nowhere. Now, if you can explain how timing and how things can emerge from nowhere, that would be an interesting power of a motor theory that can do that. And I think that ecological psychology and dynamic systems theory does a better job. So hopefully I can like make my case for you. But this thing that is moving here is unbelievable. What time is it? It's 10:28. I'll go for another 5 minutes, whatever. If you guys want to bounce, you can bounce whenever you want. I'm going to tape it anyway. So the body has crazy things. On heel strike, the heel is going to hit the ground. All right? But the ground, here, let's try to have some fun here. So here's the ground. Here's the foot. All right? Here's a heel. All right? Now the heel is going to impact the ground. It's going to create a force in this direction. Boom. But we learned in Newton's third law that for every action, there's an equal and opposite reaction. So if the heel is going to hit the ground, Jasmine, what is the ground going to do to the heel?
Like push off against it?
Absolutely. It's going to push off in what's called a ground reaction force. All right? And it's going to push in that direction. So this here, I don't know why it doesn't let me see my mouse. That is the most annoying thing. Jasmine, you can see what I'm talking about? Like, oh, that's annoying. So the ground reaction force is going to push in this direction. That's what's going to get your body to propel off of the ground. All right? Is this ground reaction force. Now, what happens if I can't create this ground reaction force? Or what happens if this here is dissipated through such a great, through such a great surface area? What happens if this force is dissipated through like a big surface area? Like it's sand. Now, the reason why sand is hard to walk out of is because the force that's going down is like shared and pushed and dispersed in this direction through each grain of sand moving, that it absorbs this force and only makes this ground reaction force tiny. It'll be like, you know, tiny. There's a very small resultant ground reaction force in this direction, so your body sinks and overcomes the ground reaction force and sinks into the sand. All right, so in any event, let's go. So at heel strike, the foot hits the ground, but then the ground pushes back on the foot and it pushes the foot away from it. All right, let's do a better drawing because that's important. So then you have this here. You have your foot. You have your heel. Now, the ground is going to push up in this direction. And let's say if I do it the right way, the heel is going to hit right there, right on the back of the heel. Now here's your ankle. And that's right here acting, this force is acting here. I'm going to try to, just bear with me, you can do it. It's acting up in this direction here. All right, the ground reaction force is ultimately pushing in that direction. Right, here's the ground reaction force. The force due to the ground. All right, that's pushing along this line, but if the ankle is here, then there is a small moment arm here. And that's going to allow the foot to rotate in this direction here. And let me put a ground in there too, so it's easier to see what I'm talking about. So here's the ground. Now the ground is pushing up, acting at a distance here. That creates a torque. That torque is going to be this torque here associated with the ground. All right, and that's going to make the whole foot want to rotate in this direction here. All right, that's the resultant motion of this particular segment here. So 10,000 times a day, I hit this heel here, and it makes this foot want to flop down in this direction. If the muscles here, if my gastrosoleus unit here with my Achilles tendon, and my tibialis anterior and the rest of my forefoot, whatever, muscles that come around here. And if these muscles here are not strong enough to overcome the torque in this direction, then my foot is going to flop into the ground. It's called foot flop. Now, why doesn't that happen? Well, for some people who have cerebral palsy, it does happen, or other muscular atrophy ailments where their muscles aren't strong enough. And sometimes you'll see a lot of those like plastic braces that allow for the heel to hit and the foot not to flop. But Jasmine, what do you think would happen if we're supposed to take 10,000 steps a day and these muscles here aren't strong enough to stop the foot from flopping and making contact with the ground right here all day, every day? What do you think would happen there?
Probably like an injury to the foot at the top there.
Absolutely.
Or like shin splints or something.
How about bunions?
Yeah.
Because a bunion is an overgrowth in the bone, right? And where would the overgrowth be coming from? Well, according to Wolff's law, it would be coming from increases in forces and stresses on the bone from somewhere. Okay, well, maybe that somewhere has to do with that increased force, 10,000 times a day, boom, boom, boom. Or maybe it has to do with the fact that the arches are flat, and then because of that, they are predominantly, here, let's even make this, let's try to make this a little bit more realistic, and I'll be done in 2 minutes, but it's kind of fun to do this. So you have your toes here, just for reference. All right, now if your foot is flat here, it's gonna make it so that your foot is more likely to roll in inversion because your foot hits inverted with the left toe, the base of the left toe coming down into the ground right here. Boom, gonna make an impact. The ground is gonna push back up. And because this foot is inverted, that means that there's an angle. The foot has an angle to the ground. This is gonna hit first. Here's the axis of rotation, right? So it's going to create a force that's going to push the foot, and the foot is going to rotate inwards because it's hitting on the toe first. It's going to force the foot into hyperpronation. And then you'll see in the big toe right here, there's a bunion right there. Right? That's because the foot is not strong enough in its peroneal muscles that are coming around here, the perineals. They're not strong enough to hold the foot in support to overcome the internal rotation of this foot. That's all because of the force of gravity creating torques in your body, storing and absorbing energy. Those motions that are happening in the foot are really important in terms of motion that happens at the leg. If your foot rotates in this way, well, your foot is attached to your ankle, and that's attached to your tibia, so it's also going to force your tibia to rotate in that direction. And if your tibia is rotating in this direction, it's attached up there to your femur, which is going to rotate in this direction, which is going to make it so that you have potential hip issues and all sorts of problems if this here doesn't go right. So sometimes what you need to do is strengthen your arches and the ankle, the muscles, but you also have to get the timing right of this particular amazing thing that's happening here. The timing has to be right. So you have to start with progression, and you have to start slowly, and you have to build up those muscles And if you can get the biomechanics to run just the right way, then, you know, people can run marathons and do stuff. But if your shins aren't strong enough, if your arches aren't strong enough, if you don't have the right shoes or the right, you know, forces going through the system, then there's a biomechanical mechanism for injury here associated with each of these things: the strength of the muscle, eccentrically, concentrically, the timing of the muscles, the structure of the foot, the arches, the musculature involved, the moment arms involved. If the force was here, you know, because of the force of gravity, it would do different things, but you strike the heel here. It creates this whole system that does these things, that stores eccentric, blah, blah, blah. I could talk forever. All right, we'll start here next time. All right, let me get out of this. That was fun. Right? That was fun. That was a good vibe. Right? That's the beauty of teaching right there. You know, it's good. I appreciate the time. No, honestly, that's the thing, man. Teaching to me is, I'm going to stop recording this. Dude, I'll tell you, I'll record this. Teaching is an amazing thing. And to be able to work with each of you, and John, when I logged on and I looked at my roster, I noticed John Lowe, and I was like, all right, that's cool. Right? And I appreciate the time that you give the class and each other and the content, and want to do what you got to do. Right? It's a beautiful thing to learn. Okay, so I appreciate you giving me the opportunity to keep working with people like you guys. All right. But sometimes you get into a lecture and you just vibe on it. So, all right. Anybody have questions?
I think you did your job really well.
Consider how all of that's happening if the brain's doing it. The brain's going to do everything all at once, all at the same time. And I could be running up a terrain that I've never been on. I could be on a moonwalk and not know. I could be on the moon. And all of these variables change, and what emerges is a different movement strategy. How? If you can explain the word emerge and where these things are emerging from, these timing patterns and all that stuff, then you have a theory of motor control, all right? And we're going to talk about dynamic systems theory and ecological psychology because it's mind-blowing, all right? All right, keep rocking it.
We out of here?
Yes, see ya.
My man, have a good day, all right?
You guys begin.